So last but not least is taking a look at what you need to kind of concentrate with regard to Chapter 4 and your upcoming unit exam. So Chapter 4 is one that sometimes students are like, do we really need to talk about this? This sounds like more like physics. And yeah, we do need to kind of talk about this to kind of put things in perspective. It's called, actually, I think in physics, called mechanics. And so we can kind of look at the motion of planets and stars and galaxies through the rest of the course and kind of know that there is an underlying understandability or predictability with regard to their motion. So there's my pitch, right? So the three terms up here with regard to motion of objects you need to be familiar with in order to kind of set the stage for talking about some things. We're probably pretty familiar with speed, how fast you're going, right? So speed would be an example of you're going 60 miles in 1 hour, 60 miles per hour. Now there is a difference between speed and velocity. So velocity gives you both how fast you're moving, and it also says in what direction you're moving. So sometimes velocity is really kind of nice to show it with a picture or an arrow or something like that. Okay, so velocity gives speed and direction. Now acceleration is change in velocity. So if acceleration is change in velocity, and velocity has the two components of speed and direction, do you see where acceleration is a change in speed and or direction? Okay, either one of those. If you change either your speed or your direction, we say that you are accelerating. So I think your book does a pretty good job up here. You see these kind of pictures of a vehicle in motion. And the first one, this is a figure from your textbook, the vehicle goes from, in a straight line, so it's not changing direction, but the vehicle changes speed from 30 miles per hour to 60 miles per hour. The next one, the middle one, the vehicle is keeping a constant speed, which I think is it 30 or 60 miles per hour? A constant speed, but it's changing direction. Okay, so that is also acceleration. And then the other one, kind of a trick question I say, so if you're going fast and you slow down or stop, are you accelerating? And a lot of times students say, no, you're decelerating, right? But actually we call that in physics, it would be a negative acceleration. So if you're changing speed, keeping the same direction, like you see that person going from whatever it is, 30 or 60 to 30 to 0 miles per hour in a straight line, that actually is negative acceleration. So momentum is kind of a fun topic, I think. So momentum has two terms multiplied by each other. Objects that are in motion have momentum. And if you want to know how much momentum an object has, you take that object's mass and multiply it by that object's velocity. Now remember, velocity is both speed and direction. So momentum has a direction component. Let's see what I was going to say next. Momentum. Objects must be... momentum. Momentum must be conserved. So there's... before I go on to that cute little figure with the man with the green hat on the roof. Okay, just let me emphasize that with regard to conservation, there's a lot of conservation going on in this universe. I think it's kind of exciting, actually. But conservation of momentum can be seen in one of those Newton's cradles, I think I said in lecture, where you have a bunch of usually kind of stainless steel balls that are kind of set up in a line, being suspended from kind of, this could be called the cradle of balls. Okay, right next to each other. They're suspended from lines. And so you take the end ball and you extend it, raise it up in the air, and then you let it fall and hit the other balls that are stationary. And then what you see is the momentum of that ball is transferred to the momentum of the ball on the other end. And it swings up, and then it comes back and hits the balls. And the other one swings up, okay? So that's a good example of conservation of momentum. All right, now on to the next small topic, right? The acceleration due to the influence of gravity of an object that you are standing on. So whether you're standing on the earth or standing on the Moon, you're going to be, a dropped object will accelerate to the surface of the Earth or the surface of the Moon. Okay, and actually that's according to the influence of gravity that's summed up in the universal law of gravitation later. But objects that are dropped will go faster and faster and faster, and depending upon the pull of the Earth or the Moon towards that onto that object. So, seeing where I want to stop this. So basically then, what we have is, independent of the mass of that object, it will go faster and faster and faster and faster at the same rate. The rate of acceleration, or going faster and faster, is actually 9.8 meters per second for every second that that object falls. And I mentioned this in lecture, but actually that rate of acceleration will be different if you're different distances from the center of the Earth. So that's why you see here, and I'll go ahead and do one more little bit of thing with regard to this. If we go ahead and round 9.8 meters per second it falls. So 9.8 meters per second is 9.8 meters per second squared. In 1 second, the objects, whether it's a feather or a hammer, will be going 10 meters per second. In 2 seconds, it'll pick up 10 meters per second, and it'll be going 20 meters per second. At the end of the 3rd second, according to just kind of the rounded 10 meters per second acceleration per second, 10 meters per second acceleration, at the end of the 3rd second, it will be going 30 meters per second. So that's kind of what I put up there. Let's see, what do we got? So I went ahead and added a new slide this semester because the concept of escape velocity has to do with gravity, and the concept of escape velocity we're actually going to have to touch on when we talk, or it's going to come into play when we talk about black holes and objects not quite so dense as black holes, called neutron stars, and even a little bit less than dense than that, a white dwarf. So in general, escape velocity is the minimum velocity an object must have to escape the influence of gravity. Okay, I think I kind of didn't finish this sentence right here, but to escape the gravitational influence, you can add influence, of the object it's trying to leave. Okay. Now I put it on your review sheet, but this is one of those things that when I tried to kind of make your exam not quite so long, it got deleted. So if you're listening to this video, good for you. The Newton's 3 laws of motion that are general for both planets and just motion of objects in general. His 3 laws of motion, you're going to want to be able to spew those back on your unit exam. Feel free to abbreviate the 3 laws as much as you'd like. The first law is that objects in motion or objects at rest will stay in motion or at rest unless acted upon by some outside force. So no mysterious moving objects, right? Some force must make them move, or some force must make them stop. Okay. His second law, if you want to just go ahead and abbreviate it, is F, like a little equation for Newton's second law of motion. Force is equal to mass times acceleration. So on your test, if you put F is equal to ma, that would be fine. Remember now that this is, if your mass stays constant, this is a way for you to understand either the forces that are acting on an object to give it a particular acceleration, or this is a way for you to anticipate the acceleration an object will experience with a certain force. Okay. The last law is that, it almost sounds like it's like a little haiku or a poem, but there is an opposite and equal, for every action, there is an opposite and equal reaction. Okay? So that's his third law of the motion of objects. Again, and these Newton's 3 laws of motion really kind of fit well with Kepler's laws specific to the planets. So, the next thing, we kind of switched gears and talk about energy in general. Energy needs to be conserved. In general, there's something called kinetic energy versus potential energy. They're kind of like yin and yang. We talked about gravitational potential energy, kind of the energy associated with position. Radiative energy, we're going to be talking more about that. We're going to talk about electromagnetic radiation. Chemical potential, a good example of that is if you burn something, you're releasing energy. It's a type of chemical reaction combustion is. Or even if you consume something and you turn that Snickers candy bar into you being able to do something. Okay, that's chemical potential energy. Thermal energy we talked about just briefly, and what I tried to kind of convince you of is if you take the temperature of something with a thermometer, okay, you're only giving one aspect of the thermal energy that that object has. In chemistry and physics, we talk about heat being the same as thermal energy, but temperature is not the same thing as thermal energy. Then with regard to temperature, temperature and density. Okay, so in order to fully describe the amount of thermal energy an object has, you need to use the thermometer to take the temperature, and you also need to know something about its density. So we talked about kinetic, according to actually the kinetic molecular theory, all matter has motion. Okay, so when you're measuring the temperature of something, you have a little probe in a beaker or a probe in your turkey, you're measuring the motion or the kinetic energy of those molecules. And then we talked about 3 temperature scales. Of course, the Fahrenheit is the one that I look at in the morning to see how cold it is, but there's also the Celsius scale, and there is the Kelvin scale, and both Celsius and Kelvin are metric scales. So there is a very important point on the Kelvin scale that actually a degree on the Kelvin scale is equal to a degree on the Celsius scale. And this important point is called absolute zero. And at absolute zero, all motion stops. So that's a very important point on the temperature scale. Nothing can get colder than that. So these 2 boxes here that you kind of see these particles going on the left one, the particles the arrow's shorter. That means they're going slower, and actually they're the cooler temperature. The one there on the right, the arrow is longer, and the particles must be going faster at the higher temperature. So that's what I mean by all matter has motion, and actually thermometers measure the temperature of that motion we call kinetic energy. So, universal law of gravitation. So you might want to put this somewhere, okay? Kind of, if you see the green and the gold ball there, that's a figure from your textbook, and they're showing you kind of the attraction that any mass, the green one on the left, has towards any other mass, the right one, the gold one shown there on the right. And you might want to jot down or understand that you're not going to have to calculate the force of gravity for any 2 objects, but realize especially that in the numerator or the top, that M1 and M2 is the mass of those 2 objects, and in the bottom, that d squared is the distance between them squared. So we say that as the mass increases, guess what? The force of gravity increases. And then as the distance increases, down there in the bottom, since it's dividing by that number, if that number becomes larger, guess what? If you divide by a larger number, the number you're calculating becomes smaller. And so kind of intuitively, as distance increases, the force of gravity decreases. Let's see. Then I have down here in the bottom right-hand corner, again, I apologize, I don't think you're able to see this quite right, where the logo of the Blackhawks is, but down there are the skaters, and remember in your textbook it has a figure of a skater with her arms out, and she's going a certain speed, and then she brings her arms in, and she is going a faster speed. Let's see, where's my, oh yeah. So I'm doing my builds down here, which, like I said, I don't think you're going to be able to see. But the point is that angular momentum has an extra term. That momentum, straight momentum, didn't. It has the radius of the circle about which that motion is occurring. So basically then, if your angular momentum is going to stay the same, if you decrease your radius, then that means you're going to have to increase your velocity. And that's what happens when she brings her arms in. Last but not least is the subject of Earth's tides, and how actually, I think one of the test questions basically says, I'll go ahead and finish these builds out here. One of the test questions says, what causes Earth's tides? And hopefully you can say something about the gravity. It's all about gravity. Our tides actually track with the position of the moon. And here in the Midwest, it's hard to say that we really have oceans to watch kind of be lifted off the Earth's surface and kind of relax back down. Lifted off the Earth's surface as the moon, as the Earth spins around and we are in the vicinity of the moon. So remember, let's see, for your test, I'll try to narrow it down for your test. What do you need to know? It could be that, and I talked about this in my slides, is that there are some especially high tides when the sun kind of gets involved and is lined up with the moon and the Earth, and it adds an extra twist or an extra pull to the moon's gravitational field, already giving us high tides. So that happens at new moon and full moon. We have especially high, what we call spring tides, when the sun is at a right angle to the Earth at the vertex. When it's a right angle, it goes sun, Earth, moon. Then actually the sun's gravitational field kind of subdues the moon's attraction to give us tides on Earth, and so we have what we call neap tides, kind of unusually low tides. That happens at the quarters, so first and third or last quarter.